So in the last couple lessons that we did, we talked about trying to find limits algebraically. And that's great. We found that with continuous functions, we can just evaluate by direct substitution. And if we get an indeterminate form, a very common tactic is to factor and cancel, or maybe use a trig identity and cancel. And that's great, but there's some limits that even once you get in an indeterminate form, factoring and cancel really just still doesn't work. And a good example of this is the limit of, as x approaches 0, of sine of x over x. Clearly the sine of 0 is 0, and 0 over 0, that's an indeterminate form. And really, you can't really do much with this, at least not using any factoring tools. There's really no trig identity that's going to help you deal with this. So oftentimes, at least at this stage in a calc class, it's simply just going to be provided to you that this is equal to 1. Okay? Likewise, this limit here is a very similar idea. The cosine of 0 is just 0. This is 0. The cosine of 0 isn't 0. It's actually 1. So we get 1 minus 1 over 0, which again, that gives us 0 over 0. And just like the last one, this is something that we can't really use the technique as we've learned so far to figure out this limit. So this is going to be equal to 0. Now, for the sake of this particular lesson that we're going through today, I don't really want to focus on actually how do we get these particular values, at least in a rigorous proof. There are a couple ways to do it. We can use L'Hopital's rule, which is a little more of an advanced technique of finding limits. There's also a nice geometric proof that if you look in your calculus textbook, you might find. And maybe in the future, I might make a video that breaks down the geometric proof. But again, that's something that it's nice to see. It's good for deductive reasoning, but it's unnecessary. So to kind of convince you, I'm going to resort to just look at the graphs. So if we look at sine of x over x, again, there is a hole here. That's not, even though you can't really see it, but you can at least see from the graphs that this is 1 and 0. Okay, so really, today is going to be more about how do we apply. So if we assume that this is true, both of these particular results, this one here and that one there, are true statements, we can use that to help us find other limits that might be a little bit more complicated by breaking it down and trying to extract something that looks like that. So we're going to do a couple examples here. So the first example is very similar to the one that we did, except we're going to have a number here. So this is sine of 5x over x. So the technique that we used to try to find this limit is that we're going to actually multiply the numerator and the denominator by 5. And when we do that, we're going to get 5 sine of 5x over 5x. So all we did was we multiplied the numerator and the denominator by 5, as we can see. So now we're going to do something called a substitution. So because x is approaching 0 here, if we substitute x with 5x, we know that 5x is also going to approach 0. So if x is going to 0, 5x is also going to 0. So we can let, we'll say theta, be equal to 5x. So that allows us to write this as the limit as theta approaches 0 of 5 sine of theta over theta. And if we remember our limit laws from last time, we can pull that constant outside. So this just becomes 5 times the limit as theta approaches 0 of sine of theta over theta. And on the last page, we showed, granted we used x's, again, the variable doesn't actually matter, that this thing is equal to 1. So this is just 5 times 1, and we know that this limit is 5. Let's do another example. So here we're going to is going to be a little bit more complicated, but we want to still kind of try to break it down to something like this. Here we want to find this limit of tangent of 4x over tangent of 9x as x approaches 0. So if I'm going to extract a sine, because that's kind of what we want from something like this, we probably want to use a trig identity. So we should remember that anytime we have a tangent of whatever it is, it doesn't matter, that's going to be the sine of that whatever over the cosine of that whatever. So we can just rewrite this as the limit as x approaches 0 of sine of 4x over cosine of 4x divided by sine of 9x over the cosine of 9x. And just like before, we can invert and multiply. So anytime you have a complex fraction like this, the best thing to do to simplify this is to write the numerator of the complex fraction and multiply it by the reciprocal of the denominator. So we're going to have cosine of 9x over sine of 9x. Okay, so from this particular venture, it's actually going to be rather useful for us to kind of separate the sine part of this and the cosine part. So I'm going to write the cosine part as its own fraction and the sine part as another fraction. So all we're going to do is we're just going to swap the location of those two guys. So this is going to be the limit as x approaches 0 of cosine of 9x over cosine of 4x times, and we're going to actually write this as two separate limits because remember that when you have two limits and you have a product, we can write it as the product of two limits. So this will be as x approaches 0 of sine of 4x over sine of 9x. Okay, so it turns out that this is actually fully determinant, this first limit here. Okay, if we plug in 0, we know that the cosine of 0 is 1, so this is just going to be 1 over 1. This whole thing is just 1. So really, this is just going to be a matter of finding this particular limit here. So what we actually want to do, okay, the little trick that we're going to do here is we're going to multiply the numerator and the denominator of the second fraction by x. Okay, because we're looking for some kind of sine of something over x, and when we do that, we can actually break this down. So we're going to actually break this into two more limits. The limit as x approaches 0 of x over sine of 9x times the limit as x approaches 0 of sine of 4x over x. And this second limit here should be just equal to 4 because we can kind of do what we did up here. The only difference is that there's a 5 here, so we can put a 4 here and a 4 here. We can do our substitution just like we did there. And this thing is just going to be equal to 4. Okay, so we know that our final answer is going to be 4 times whatever that second limit is. So let's just look at that second limit a little bit more carefully. And one thing that we can do here is we can actually kind of rewrite this as the limit as x approaches 0 of 1 over. So we're going to kind of do the reverse of the inverting and multiplying, sine of 9x over x. And this, by the quotient rule, is just going to be the limit as x approaches 0 of 1 over the limit as x approaches 0 of sine of 9x over x. So if we do this, we already know that kind of by the same vein that we did up over here, we can multiply by 9 in the numerator and in the denominator, and we know that this thing is going to be 9. So that's going to be 1 over 9. So we know that the second limit here is just 1 over 9. So this is just 1 over 9 times 4, or 4/9. So again, this was a little bit more of a complicated example, but again, just with those little extra tools, knowing that the limit of sine x or sine theta over theta is equal to 1, we can expand our toolbox to be able to solve these more complicated trigonometric limits. So that's going to be it for today. As always, I hope that this video was helpful, and as always, take care.